Okay, we're going to look at the work-energy theorem, which says the net work done on the object by the net force acting on the object will change that object's kinetic energy. Remember that a change is a final quantity minus an initial. This is not a new theory for us. It's something we've actually been working with the whole time. So let's weave together some of our old kinematics information, with the equations that we'd use on the board. Here we have a 1,000 kilogram car. That's a mass, and it's traveling for 6 seconds, that's our time, over a distance delta x of 90 meters. So here it maybe is x initial of 0 and an x final of 90. It starts from rest, v equals 0, and goes to some final velocity. All right, what acceleration does the car experience? Okay, so here we can say 90 equals, and plug in our time as 6 seconds. Acceleration comes out to be 5 meters per second squared. It then asks for the final speed. All right, so our car reaches a speed of 30 meters per second, or about 60 miles per hour. The net wants to know what's the net force acting on the car. That's our last unit. We can say F net equals ma, also written as sum of the forces equals ma. We know the m is 1,000 and the a is 5. Now it wants to know how much work is done on the car. This is our new concept. Net work is going to be the net force times the distance. So here we have our net force of 5,000 newtons times the distance that our car travels, 90 meters. And if we multiply those together, it comes out to be 4,500,000 Newton meters work done on our car. Now, the change in kinetic energy of our car will be Ke final minus Ke initial. And so that will bring us to 1/2 m V final squared minus 1/2 mv initial squared. But the v initial is just 0, so the whole term for the initial is 0. So let's do this out. So we get 500 times 900, which comes out to be 450,000 joules. Coincidence? No. This is the fact that net work is a force times distance and will change a kinetic energy. That's work-energy theorem. We've actually been using this concept for way longer than this unit. Let me show you. Work is force times distance. Delta Ke is 1/2 mv final squared minus 1/2 mv initial squared. Okay, replace force with mass times acceleration. This then allows us to cancel out the m's. Then we'll multiply by 2. That will allow us to move that half to the other side. Then we have minus v initial, so we'll add v initial squared to the other side. And with that, you'll see we have v final squared, we usually put it on this side, equals v initial squared plus 2ad. And most times we write d as delta x. Bam! Work is changing kinetic energy is actually the v final squared equation you've been using the whole time. You've been using energy and you haven't even known it. Let's practice some applications below. Okay, so here's a basic problem. How much work does it take to bring a 2 kilogram object from rest to a speed of 2 meters per second? You're going to say work net. It's a force times the distance, but it's also a delta Ke. So go ahead and write out your delta Ke. 1/2 m v final squared minus 1/2 m v initial squared. That gets you 4 joules of work, or Newton meters. Okay, so next we're going to look at a car. So you can do 2 and 3 if you like, but we're going to look at a car under some different circumstances. So we're first going to take a car, we're going to crash it into a wall, and then we're going to stop the crash in 0.5 meters. We're going to do that same crash of 14 meters per second into a wall and stop it, but take 2 meters to slow it down. So think about tossing an egg, taking 0.5 meters to bring that egg to rest once your friend tosses it to you, or taking 2 meters, right, backing up and cradling it. Next, we'll double the speed of the car to 28 meters per second and stop it in that same distance as the previous problem, 2 meters. What do you think will change between the works and the forces during these problems? Let's start out doing the first one. So how much work is done? Work net is delta KE. So here we have 1/2 m V final, which is 0th, minus 1/2 m V initial. All right, so our work actually comes out to be a negative number here, negative 156,800 joules. What this means is that the stopping work, a slowing work, a work with a negative delta KE, a work where the force and displacement are opposite. So this answer is just giving magnitude, which is fine. Okay, well, what force would be applied? So let's take that magnitude of work, 156,800, and let's say that work is a force times a distance. So force and distance, 0.5. So we get a force applied on a car, ooh, this is a pretty large force, of 313,600 newtons. Oof, that sounds painful. If we increase the stopping distance to 2 meters, what do you predict will change about the work done on the car while coming to rest? What do you predict will change about the force on the car as it comes to rest? Let me show you this interesting YouTube video of Minutephysics to help you think about it.
Gasoline has approximately 56 megajoules of chemical energy per liter, which is more energy than you get from exploding the same amount of TNT and is enough to power a toaster for a full day. Cars work by burning gasoline to convert that chemical energy into the kinetic energy of motion of the car, though almost 80% of it is lost as heat in the engine. Still, 20% of 56 million joules is a lot of joules. To give a direct sense of gas to car conversion, it takes about 5 teaspoons of gas to accelerate a 2-ton car to 60 kilometers per hour, and about 1/3 of a cup more for every additional minute you want to keep it going at that speed. That might not sound like a lot of fuel, but the energy of a car moving 60 kilometers per hour is equivalent to dropping an elephant, or stegosaurus, from the top of a 3-story building. And in order for the car to stop, all that energy has to go somewhere. If the brakes do the stopping, they dissipate the energy by heating up. Or in the case of a collision, energy is dissipated by the bending and crumpling of metal in the outer areas of the car. And just like how smooth braking is nicer than a quick, jerky stop, cars are carefully designed to crumple when they crash, in a way that lengthens the duration of the impact so that stopping requires less intense acceleration. Lots of acceleration over a very short time is not good for soft human brains and organs. However, people don't like driving cars with Pinocchio-length noses, so most cars only have around 50 centimeters of crushable space in which to dissipate the energy equivalent of our falling stegosaur. That means that while crumpling, they need to maintain a resistive force of about 1/4 of the thrust of the Space Shuttle main engine. Over half of the controlled crumpling work is done by a pair of steel rails connecting the front bumper to the body, which bend and deform to absorb energy and slow the car. Most, and in ideal circumstances all, of the rest of the energy is absorbed by the deformation of other pieces of structural metal throughout the front of the car. This meticulously engineered destruction allows a crashing car to decelerate at a high, but reasonable and constant rate, just slightly over the acceleration experienced by fighter pilots or astronauts in centrifuge training. As comparison, if cars were super rigid, like they were before the 1950s, and didn't crumple, they would stop so fast that they would undergo acceleration 15 times what fighter pilots experience in training, which is definitely not good for your internal organs. Thankfully, engineers have learned to make cars with crunchy crumple zones surrounding a rigid safety cell, because fully rigid cars are not good for fighter pilots or anyone else. Except maybe robots.